Hi, Chris Good here. We are in SPSS and we're going to do a repeated measures analysis of variance, and this is going to be the one-way version of the repeated measures analysis of variance. So we will choose repeated measures from the general linear model section of the Analyze menu in SPSS, while the bushtucker.sav data file is selected. So if you'll remember, we're measuring latency to retch after eating one of these four animals or parts. So we're going to say animal is the within subject factor name, and there's four different ones, so we'll say that there's four levels. So this is the default window that opens when you start the repeated measures general linear model, and you need to define those factors. We only have one factor here with four levels. So we'll add that, and then we'll click on the Define button, which gets highlighted in this version of SPSS. All right. So you're presented with a dialog box right here that says, I don't know, question mark, what the four levels that you just specified for this single factor are. And because they're repeated measures data, we're measuring them as they were four different independent variables within all of our participants. So we'll just drag these over, and I'm just going to keep this order. And when you press OK, that'll run the repeated measures ANOVA on those data, tell you whether there's an overall effect of animal for these participants in terms of time to retch after they ate them. Let's select a couple of things though. So we could do contrasts to determine whether where any significant differences lie. If we do get an overall effect, it defaults to polynomial, but we can choose well, a repeated contrast would compare 1 to 2, 2 to 3, and 3 to 4. These don't go in any particular order, so that would be fine. So let's try the repeated contrast for this one, and we'll go on and select some other options. Notice that if you click on post hocs, you're not allowed to run post hoc tests on these repeated measures data. One of the assumptions for pretty much all of these post hoc tests is that your observations are independent, and they're not. In this case, they're from the same person. So we don't really meet the assumption for a lot of these post hoc tests. You could still do them. You could program syntax to do them, I think. You could also do them by hand if you really, really wanted to know. But there is a way to compare means from each one of these three groups in the options menu. So if you click on options and you select your within subjects factor, the only factor in this study, drag it over to the display means, you can tick this little box that says compare main effects. And this will do paired comparisons for every pair in your list of levels for that factor. And you can choose from a number of different adjustments for multiple comparisons. Let's go with the conservative Bonferroni just for this example. I want to be able to see the codes for the contrast that I selected earlier for the repeated contrast, so I'm going to say give me that transformation matrix, which will give me the contrast codes that SPSS uses. And let's go ahead and ask for those descriptive statistics as well. When we hit continue, we'll see the output file generated after we click OK. All right. So SPSS tells you what it did. It ran the general linear model. It has a within subjects factor with 4 levels. They're the descriptive statistics that we asked for. And then it gives you the results of multivariate tests. So there's 4 different multivariate tests that are run. We're going to get to this in a later video. For right now, I want to focus on the univariate repeated measures ANOVA that we just ran. So really the first test of interest to us in this case is here, Mauchly's test of sphericity. Remember, sphericity refers to the equivalence of variance of different scores where we're comparing the means, we're comparing the different scores in stick insect versus kangaroo testicle, for example. So we generate a distribution of difference scores by subtracting every participant's response in this condition from this condition, and compare those difference scores to the difference scores that result from another subtraction. So 1 minus 2 versus 1 minus 3, or 1 minus 2 versus 2 minus 4, right? And we do this for all the comparisons. Those distributions of difference scores, it's the difference scores that have to have homogeneity. And that's a special case of something that we call circularity, but we will come back to that in more detail in a different video. The bottom line is that if you fail this test by having a significant value here, as we have, not all is lost. You can make an adjustment to the degrees of freedom in the repeated measures ANOVA using this estimate of the sphericity, the greenhouse geyser. It calculates the measurement of sphericity as epsilon, and it's going to have a value between 0 and 1. When that value is below, field recommends around 0.75, you should stick with the greenhouse geyser adjustment to the degrees of freedom. It's quite conservative, but when you have a deviation from perfect sphericity as great as this, then you'll want to go with this one. When you get an estimate above 0.75, then Huhn-Felt also provides an estimate of sphericity that is used to adjust degrees of freedom. And you can see that in the table below where we get to the tests of within subjects effects. So when either one of these is above 0.75, we'll go with the less conservative Huhn-Felt because we're closer to meeting the requirement for sphericity. We're closer to meeting that assumption. When it's below 0.75, right, as we see both of these estimates of sphericity are below 0.75, we'll stick with the more conservative greenhouse geyser. At least that's what field recommends. So on to the test of within subjects. Had we met this assumption of sphericity, we would have gone with sphericity assumed. For this, the repeated measures, the within subject factor that we have here, degrees of freedom would remain unadjusted, and this F value, which you'll notice is the same for all these adjustments, because it's not the F value that changes when you make adjustments to degrees of freedom. It's the theoretical distribution of F that changes when you make adjustments to the within subjects degrees of freedom right here. So while we would have rejected the null had we met the assumption of sphericity, we had a significant deviations from sphericity of such a magnitude that requires the greenhouse geyser adjustment to degrees of freedom, which again changes the distribution, the theoretical distribution of F that we're comparing this value to, such that it's no longer significant. So we don't have a significant finding here. We'll fail to reject the null. You'll notice though, and again we're going to do this in another video, the multivariate test passed. So multivariate tests, just for now, know that they don't require the assumption of sphericity. So if you violate it, you can actually go to these, and we would have rejected the null in this case using any of the multivariate tests available to us. So we have here a finding that's kind of on the borderline. It illustrates one of the main problems with hypothesis testing statistics is that you're left with an either-or decision at the end. It's significant or it's not. We've gone ahead and said that it's not, but you know what? Under some circumstances, it could very well be. So let's take the opportunity then to say, well, if we had rejected the null and if there were a significant overall effect of animal type on our dependent variable here, how would we proceed? There's the within subjects contrast that we asked for, And here are the contrast codes, right? So in this first comparison, it was stick versus kangaroo parts. And so level 1 versus 2, that was a significant difference. We also compared 2 and 3. So that was 2 versus 3 was kangaroo testicle versus fish eyeball. Not significant there. If we go back and look at the means up here, they were actually very close together. Finally, we did level 3 versus level 4, so eyeball versus grub. These were the only 3 comparisons that we made in that repeated type of contrast, and that also was not significant. So 3 versus 4 up here in the means, right, was fish eyeball versus witchetty grub, and those were pretty close together as well. This is really the one that stands out. Stick insect takes a long time compared to these other 3, but we didn't make those comparisons. We only compared this versus the other versus one other group. In the contrasts, if we go down below the transformation coefficients and get down to the estimated marginal means that we asked for, here's where we get to those pairwise comparisons. And remember, these have been adjusted using the Bonferroni adjustment for those multiple comparisons. We get all of the possible paired comparisons, 1 versus the rest, 2 versus the rest, 3 versus the rest, etc. And we can see that 1 versus 2 pops out as significant. So insect versus testicle, that supports the contrast that we found earlier. But 1 versus 3 is also significant. So compared to number 3, which was the fish eyeball, stick insect takes longer. And with the adjustment for multiple comparisons, 1 versus 4 is not significant. So this question up here of is 8.13 significantly different from 5.75. That with that adjustment for multiple comparisons, it's not significant. Okay, those are the things that we wanted to look at in the repeated measures analysis of variance. We will try another one that's a 2-way repeated measures analysis of variance in a separate video. We'll see you next time.